Welcome to this explainer. Today, we're going to tackle a super common, incredibly expensive, and honestly, pretty dangerous mistake in off-grid solar engineering. It's a trap so many beginners fall into, so let's just dive right in and uncover the exact engineering logic the pros actually use to size off-grid inverters. Let me pose a simple question to get us started. If you calculate that your home needs exactly 4.7 kilowatts of power to run everything at once, what size inverter do you actually need? Well, before you go and click buy on that new unit, we really need to talk about why your first instinct to just match those numbers exactly is probably a terrible idea. To solve this, we're going to follow a logical, step-by-step approach. We'll cover the autonomous villa audit, the dangerous beginner's trap, the 50 to 80% golden rule, a reality test, and finally, the final engineering verdict. All right, step 1, the autonomous villa audit. To figure out the right equipment, we absolutely have to start with a realistic scenario. Here's our test case: a small, fully autonomous villa designed to operate entirely off the grid. And look, our goal here isn't just to make the lights turn on for a day. We want to build a rock-solid system that functions safely and reliably for decades. Okay, so imagine every single appliance in this house is switched on at the exact same time. Doing the math, that gives us a maximum expected electrical load of 4,700 watts, or 4.7 kilowatts. This number right here is our absolute baseline. Picture a crazy busy morning, right? The heavy hitters, like the washing machine, are pulling 2,000 watts, and the water pump takes another 900. Add in your kitchen gear at 1,000 watts, plus the lighting, TV, router, and the fridge, and boom, we hit that precise 4.7 kilowatt peak. That represents a 100% maximum load for this specific home.
Which brings us to step 2, the dangerous beginner's trap.
Now that we've got our 4.7 kilowatt baseline, we immediately run into a huge logical fallacy. I mean, it feels like common sense to just go online and buy a 4.7 kilowatt inverter to match, right? But the absolute rule here dictates you should never choose an inverter that exactly matches your maximum calculated load. Think about the sheer heat being generated. If you pull 4.7 kilowatts of power through a 4.7 kilowatt unit, you're subjecting those internal electronics to continuous maximum thermal stress. You are literally turning your incredibly expensive inverter into a space heater. It's really just a matter of time before something melts or entirely fails.
So how do we fix this? Step 3, the 50 to 80% golden rule.
To avoid completely burning out the hardware, professional engineers follow a very strict protocol. You can think of this optimal window as the holy grail of off-grid design. Basically, your normal maximum load should always fall somewhere within the 50 to 80% range of your inverter's rated continuous power. An inverter should never operate constantly at its absolute limit. Think of your system capacity like a dashboard gauge. That green zone in the middle is your optimal engineering window. Pushing up into the red zone, like running at 90 or 94% capacity, is exactly like driving your car on the highway permanently stuck in first gear. The engine is going to scream, it's going to overheat, and eventually, it'll die. The exact same physics apply to your power electronics. Staying securely inside that sweet spot unlocks 5 massive system advantages. You get much lower operating temperatures, higher conversion efficiency, and dramatically improved system reliability. Plus, and this is absolutely crucial, you gain the headroom needed to safely absorb sudden motor startup surges. All of this guarantees a significantly longer lifespan for your hardware. Let's see this in action with step 4, the reality test. Let's put this theory directly into practice for our villa. Say we look at a 5 kilowatt inverter. 4.7 kilowatts divided by 5 forces our hardware to run at a massive 94% capacity. That puts us right in the danger zone. But if we step up to a 6 kilowatt inverter, that puts our max load at 78%, nestled perfectly right at the upper edge of our optimal window. The contrast here is super stark. With the 5 kilowatt unit running at a 94% base load, just think about what happens when that 900 watt water pump suddenly kicks on. That instant current spike will trigger the overload protection, and boom, your entire house shuts down. But with the 6 kilowatt unit, that comfortable 22% reserve easily absorbs the power spike, keeps the internal temperatures optimal, and even leaves you some headroom if you want to add a new appliance later on. Which naturally brings us to step 5, the final engineering verdict. Let's finalize this design choice. For our calculated loads, the 6 kilowatt inverter is clearly the only correct engineering choice. It just wins across the board. Longevity for the electronics, solid reserve for future additions, high tolerance for those heavy water pump startups, and complete adequacy for this specific home's load profile. So for your own off-grid projects, please take away these 3 crucial executive steps. Step 1, always audit your peak connected load first. Step 2, never match that calculated load exactly. And step 3, always target that 50 to 80% optimal engineering window. Doing this will absolutely guarantee the longevity, tolerance, and safety of your system.
But in the fascinating world of systems engineering, solving one problem almost always creates another. Because we made the smart choice to step up to a 6 kilowatt inverter, we fundamentally changed the requirements for our storage bank. Significantly increasing our inverter power means the battery current is going to increase dramatically too.
And that leads us to a massive question to leave you with. If stepping up to a 6 kilowatt inverter safely protects our house, but fundamentally dictates a transition to a 48-volt battery system, how does that single choice completely alter the physics, safety, and cost of our storage bank? Well, we're going to tackle that exact hurdle in our next explainer. Until then, remember to always leave a healthy buffer in your electrical builds. Thanks for hanging out and learning with us.